Alright, this screencast is going to focus on continuing to draw Lewis diagrams, but this time we'll focus on Lewis diagrams for ions. The nice thing is that you follow the exact same steps that we just followed before, so hopefully those practice problems went well. So step one for us is going to be complete all the previous steps that we reviewed. The only thing that's going to change is when you get to the total electron count. We know that if something has a negative charge, that is because it has gained electrons. So if something has a -2 charge, that means he has 2 additional electrons than if he were just neutral. So what we would do at the end would be to add 2 electrons to our total electron count. If something has a positive charge, that means it has lost electrons. So let's say we have a +3 charge, like aluminum. That means he has lost 3 electrons, so we would actually want to subtract 3 electrons from its total electron count. So the next step is just to adjust your electron count based on whether you have a cation or an anion. So that's really the only change that you make to the 5 steps above. And then the last step, because we want to let people know that, hey, this isn't a neutral compound, this is something that has gained or lost electrons. The last step is to place brackets around the compound or the structure and write the charge in the upper right hand corner. So let's do these 2 examples so you can kind of see what's going on. So for Cl04 minus, the -1 means he has gained an additional electron. So if we go through our steps, chlorine has 7 valence electrons. We've got 4 oxygens. Each of those oxygens has 24. Or sorry, each of those oxygens has 6, which gives us 24 from that. And then the -1 means that we need to add 1 to the total electron count. So if I do the math on that, I've got 7 plus 24 plus 1. So really I've got 24 plus 8, so that gives me 32 electrons to work with. That's really the only change you have to make other than putting the brackets on at the end. So our central atom between 1 chlorine and 4 oxygens, the one that's by itself is the chlorine. So he's going to go in the center. I'm going to attach the oxygens with single bonds. And that just used up 8 of my electrons, so I need to keep track. I had 32, I used 8, so I have 24 electrons left. I'm going to give them to my terminal atoms first before I worry about my central atom. So each of these oxygens are going to get 6 electrons. And last step, most important, make sure everybody has an octet that wants an octet. Each oxygen has 8, the 1 chlorine in the center has 8, so everybody is satisfied, and I'm out of electrons. So my last step, again, is just to let people know this isn't neutral Cl04, this is actually the Cl04 -1 ion. So we'll just put that charge out to the side. So pretty straightforward and not too different from what we did before. NH4 plus, we've got 5 valence electrons from nitrogen, plus 4 times 1 from each hydrogen, and then that +1 means he's actually lost an electron, so we'll subtract that electron off. So the math ends up being 5 plus 4, and then -1. So we have 8 electrons to work with in this case. Again, the central atom is no big mystery. Nitrogen is going to go in the center. We're going to assume single bonds and attach those hydrogens. And that just used up my 8 electrons, so I'm out of electrons. So if I look, my hydrogens are an exception. They're good with just their 2, and then nitrogen has a nice octet around it, so we're fine being out of electrons. Last step, put brackets around, and we have a +1 charge. So that's how we draw Lewis diagrams for ions. If you wanted to try some of those, if you look on the back of your notes, number 6 is an example of an ion, number 11 is an example of an ion, 12 is an example of an ion, and then 13 and 15. So if you want to pause this screencast, go and try those, make sure they go okay. We're going to continue on with resonance and look at some examples of resonance as well. So if we go back, let's actually go back to this one, because I didn't ask you to draw this one yet. So SO3, let's do that one together. We've got 6 valence electrons from sulfur plus 6 times 3, because you have 3 oxygens. So we have 6 plus 18, so we have 24 electrons to work with. No worrying about a plus or a minus, because no plus or minus is written, so we assume that it's neutral. So if I go and I draw this one out, we put sulfur in the center. We assume single bonds. Again, it doesn't matter how you place these oxygens around it. You could have had one up there. Doesn't matter. I just used 6 electrons, so I have 18 left. So if I satisfy the terminal atoms first, each of these guys needs 6. So that uses up all my electrons. So for SO3, if I look at that S, he's definitely not satisfied. And he's not an exception to the octet rule, so he does need to be satisfied. So I have lots of choices, you know, when he's not satisfied, and your only option is to form multiple bonds. And if he's already has 6, really we just need 1 double bond to satisfy that. So it doesn't matter who you pick. I'm going to take this electron pair right here, and again we'll move it so that both the oxygen and the sulfur have access to it. So what we've done there is we've formed a double bond. And now if we look at sulfur, right, he's got access to 8 electrons. So his octet is satisfied. But if you think about it, you know, I chose the oxygen on the left. You could have just as easily picked this oxygen in any of these electron pairs and moved it. Or you could have picked this guy on the right. So when that happens, when you find yourself making a choice about who is going to double bond, that is a molecule that exhibits what is called resonance. So resonance is really just a fancy term for saying more than one correct Lewis diagram can be drawn. So we'll say a molecule exhibits resonance when more than one correct Lewis diagram can be drawn. So it's nothing super mysterious. It's just the fact that, you know, when I'm drawing these compounds out, if SO3, if any of those oxygens can triple bond, really what I end up with is I have one SO3 that looks like this, which is like the one we drew on the back, or another structure could be, I'm going to double bond the oxygen on the right and leave these other 2 to have single bonds. Or our last option is to have the oxygen on the bottom form the double bond. So sometimes questions will ask, well, how many resonance structures could be drawn for this? So the little double arrows that I'm drawing, that's just the way some textbooks represent it. Sometimes they'll even put these in brackets and put the little double arrows in between it. Again, not showing that they're ions, but showing that there's three separate structures that you can draw. So this would be resonance structure 1, this would be resonance structure 2, and this would be resonance structure 3. Now it doesn't matter who you call 1, 2, and 3, but basically you're coming up with all the possibilities. If you keep studying chemistry, if you go on to second year chemistry, you'll find that, so in order to know how many resonance structures you can draw, just look at all the possibilities. And so for this one we had 3 oxygens, each of them could double bond, so that's the reason we have 3 resonance structures. If the question doesn't ask you anything about resonance, or doesn't say, hey, remember to show all possible resonance structures, then you would have been totally fine just drawing this one structure and calling it a day. But if they do ask you to include all possible resonance structures, that's when you would want to do that. So this wraps up Lewis diagrams for ions and what is resonance. So if you want to practice the rest of these that are on the back side, again, SO3 is the one that has resonance. Check to see if any others have resonance. So if you double bonded somebody and you had to make a choice there about who you double bonded, then see what the other possibilities are and finish up this practice and make sure you're good on those.